All right, so we've got norm captured, length captured at 2 dimensions. Let's extend up to 3, where we also can visualize to see if we can notice a trend between the 2-dimensional case and the 3-dimensional case. So for the sake of just getting an example, let's use a vector like, I don't know, 1, 2, 7, or something like this. This is going to be, let's call it vector C, and our goal is to find the length of the vector C. So then you say, okay, well, how are we going to do this? Well, I mean, heck, you've got a vector here, which, as you know, the 1 corresponds to the movement along the x-axis, the 2 along the y, and the 7 along the z. Well, this vector, which is an arrow, a single arrow, in the direction of a movement 1 along the x, 2 along the y, and 7 along the z, would have some length. We ought to be able to take a ruler to that in some sense and find the length of that vector. Well, to do that, let's just imagine we've got the 3-dimensional space here, where we've got the x-axis, we've got the y-axis, we've got the z-axis. 1 unit along the x-axis, that would be out here like so. 2 units along the y-axis, that would be along the y-axis like so, and then 7 units along the z-axis is way up there. Now, there's going to be a vector associated with that movement, and that vector is our vector C. There it is. We want to find the length of vector C. Okay, now, to find the length of vector C, man, how are we going to pull this off? Well, to think about it here, man, if we draw a diagonal in the xy plane, because you see in the xy plane we go 1 unit to the right and 2 units back in the y-axis. If I draw in this diagonal in pink, if we just knew the length of that diagonal, we'd have a Pythagorean triangle, wouldn't we? Because if you're in the xy plane and this movement of 7 is in the z-axis, you know the z-axis is perpendicular to the xy plane. Hell, that's how you construct your 3 axes, each of them 90 degrees perpendicular to one another. So if we just knew this diagonal length, let me call it d, well then we'd be able to use Pythagoras to find the norm. Because using Pythagoras here, we'd know that d squared plus 7 squared equals the norm that we're after squared. So if we just knew what d squared was, we'd be in business. But we do know what d squared is if we think just in the xy plane. Because if we only look in the xy plane, we've got a picture with a movement of 1 and a movement of 2, but that movement of 1 in the x direction and that movement of 2 in the y direction are perpendicular by virtue of the fact that the x and y axes are perpendicular. So when you're looking in just the xy plane, you've got a Pythagorean triangle, and we know that 1 squared plus 2 squared equals d squared. But check it out. If you know that 1 squared plus 2 squared is d squared, that gives you the very unknown that you didn't have in your effort to find the norm of C. So, plugging in 1 squared plus 2 squared for d squared, we get 1 squared plus 2 squared plus 7 squared is the norm of C squared. And now, did we want to know the norm of C squared? No, we were hoping to find the norm of C. Well, if you know the norm of C squared and you want the norm of C, take the square root, and in doing so, the square root of 1 squared plus 2 squared plus 7 squared is the norm of C. But then reflect upon that for a second. Because where did the 1 come from? Well, that was just your movement along the x-axis. Where did the 2 come from? That was just your movement along the y. The movement of 7, that was your movement along the z. So if in general, your vector was not 1, 2, 7, but C1, C2, C3, you could describe the length of that vector as the square root of C1 squared plus C2 squared plus C3 squared. So in general, in 3 dimensions, the length of your vector is the length of C1 squared plus C2 squared plus C3 squared square rooted. Okay, so now we've got ways to describe very concretely what the length is of our vectors in 2 dimensions and our vectors in 3 dimensions. And now, to develop this notion of norm, we want to generalize our notion of length to dimensions possibly higher than 2. So what we're going to do here is assume that B is an n by 1 matrix. So you know that a little letter with an arrow over it is signifying an n by 1 matrix, and you know that n by 1 matrix could have any number of entries in that single column that it has. So let's just imagine that instead of 2 entries or 3 entries, we had n entries. Well, if you take this notion of length and extend it now to those n entry vectors, you note in both cases, you just took each entry, squared it, summed up the result, and square rooted. So you could do the same thing here. Take each entry, square, sum up the result, and take the square root. So here is a notion of length in n dimensions. Now, since once you go beyond 3 dimensions, you don't really have length per se, but sort of length in some sense, let's just call this length norm. So norm is a word to describe length, even when you extend beyond dimensions where you have concrete notion of length. And how do you compute the norm of any vector? You just take each of its components, square them, add them up, and take the square root. So, as an example of this, if you wanted the norm of the vector, let's say 1, 2, minus 1, 4, you could compute that. How do you do it? The norm, as it always is just the square root of the sum of all of the components squared, and when you add this up, you're going to get what? 1 plus 4 plus 1 plus 16, so that's square root 22. Whatever that number turns out to be is whatever the norm of this vector is in 4-dimensional space, in effect, whatever the length of that vector is in 4-dimensional space.